just thank you for inviting me to this nice event, this nice place. Actually, I believe that today it also raised the level.
This is Anatoli Juditsky.
Yes. So I expect that this will be even
Who
better.
doesn't know Anatoli?
No. Actually, well, as the poet said, that okay, the whole Russia will remember this day forever. Basically, I think about it in tonight. Okay, so this is a joint work with Anatoli Juditsky and Anatoli Juditsky. And okay, so just thinking about historical motivation, so imagine that you have a Russian Cossack which are positioned around the forest and they try to find a lost French soldier there, and basically they are lazy and maybe they celebrated the previous night, so they don't want to enter the forest, and the question is how they communicate between themselves just to raise their probability of finding the soldier in the forest, but maybe the soldier is not there. So as I said, they celebrated, so their perception is quite perturbed. And the mathematical formulation of this problem...
I'm sorry, I already don't know what the problem is. Can you actually, with no jokes, what is the actual problem? You have how many people on the... What is happening here?
Okay. So you have a sensor array, say, which are positioned in this picture, this example, they're positioned on their sides of the square, and you have 20 sensors uniformly distributed, and basically you have the grid, and you expect that some event can be produced in the grid, and an event which is produced in the grid produces a signal, okay? And what you see is just the response of sensitivity, the contour plot of their sensitivity of the sensor. Just we can come to mathematical formulation of the problem. So we assume that we have a grid, okay? And basically, an event on the grid produces a signal which is known up to the amplitude, right? So we have a family, a known family of vector E of I, which corresponds to events on each position on the grid. And basically, we assume that the signal may be contaminated by some nuisance, which is the ground signal. And our observation is as follows. Actually, we have a vector which is a linear transformation of the signal plus nuisance. All right? And then we draw a random variable which with distribution which is parameterized with this vector. Okay? So the matrix of sensor responses is known. So the transformation from the signal space to the observation space is known. And this distribution, the family of distribution is known. But the parameter mu and then S and G are unknown.
So your signal is normalized, the E is normalized?
Yeah, the E is normalized, but we don't know the amplitude. So maybe the amplitude is 0, so there is no useful signal, or the amplitude is right. Okay, so our objective is to just, we don't want to estimate the signal, we want just to say if there was, in this situation, if there was a signal or there was no signal at all. So our hypothesis will be that there is no signal, only the nuisance probably. Okay, so this, okay, if we want to separate the null hypothesis with the signal hypothesis, we have to separate basically the two sets. The set of null hypothesis for this end, to this end we assume that the linear transformation of the signal is not, it does not vanish. And then the amplitude of the signal under an alternative, that when we assume that there is a signal, is bounded from the loop. Okay? And our problem is to separate the two hypotheses, that there was no signal and there was some signal at some point of the grid, and the risk of the test of decision between these two hypotheses, we will measure like the maximum probability of wrong answers, so the probability to say that there was no signal when there was signal, and the probability of saying there was signal, there was none. And our goal, of course, is given this risk, okay, we want to construct a test with the maximum as possible, which will detect maximum as possible, as large as possible hypothesis H1. Okay? So this corresponds, the largest hypothesis H1 corresponds to the smallest parameter rho, which is the lower bound on the amplitudes of the signal. So here, rho basically it's a vector, okay, of if the signal has, if there are n possible events, then for each event we will have probably different value of rho.
You assume there's going to be one event, or there may be
Oh, there is
weak
only one
events?
event. Okay, in this situation there is only one.
So we can imagine also that there's some channels and signals, and so you have several channels, and you have to detect whether the signal and some of them or not.
No, only one.
Only
The useful signal maybe in this setting there is only one signal. Okay, so a particular case of this setting is the classical problem of detection of the jump of jump in derivative or whatever signal non-signal in non-parametric situation. So basically, which amounts to there is huge literature on the subject, and basically it amounts to the following observation scheme: that you have your observation, which is the useful signal. So imagine the jump in the derivative, and there is some nuisance signal, which is smooth, some smooth component of the function, and then you do the transformation, and basically from the space of derivative you go to the observation space, and everything is contaminated by white noise. All right, so here you have the convolution. Here the transformation A is constructed the following way. Imagine we have defined the convolution kernel, okay, of length t, and then the output, this transformation of A from the signal to the observation space, is just the convolution, okay, with this kernel. So basically, if you have m observations, then the state space, the length of the signal will be n, which is n plus t minus 1. Okay. So basically, what we want in this situation is to detect if there was a jump or there was none. And okay, so we want exactly to solve this the kind of problem I described below. So the signal is known up to the amplitude, and we want to know if the amplitude was 0 or was larger than some threshold. Okay, let us make some assumptions. We will make very basic assumptions, and okay, we will assume that okay, we have these three assumptions to people who know a little bit about statistics. It means that basically we have an exponential model. Okay, it's an exponential family of distributions, and okay, so we work with exponential family of distributions, and we will add to this one assumption which is much less trivial. Basically, what we will assume that the function, okay, of this form. So for any function which lives on this space, of logarithms of ratios of densities. So if we compute this functional, we want it will surely be convex in phi, and we want it to be concave in mu. All right, this is an assumption. And if these assumptions, so if we have an exponential family with this assumption verified, we will say that this is a good observation. All right, on the top of this, we will assume that we have two sets. So we have, sorry, we have two Euclidean spaces. We have two sets, X in one space, Y in the other space, and we have here linear transformation, linear mapping A from from X to some observation, m-dimensional observation space. We have another linear mapping from Y to another observational space. And we assume that the images of X and Y belong to our set M, and our objective is to decide between just two methods. All right, so we have an observation drawn from this distribution with parameter mu, and we want to decide between two hypotheses that the underlying X which produced mu was belonging to X, so this is our hypothesis Hx, or it was belonging to Y, which is our hypothesis Hy. Okay. So the risk of the test is I've just said, so this is just the formula explaining what was said. So they basically, we define two probabilities of wrong detection. So the test rejects the hypothesis HX when it is true, and the probability of rejecting the hypothesis HY when it is true. And we will define the risk of the test as the maximum of these two probabilities. Okay, we will be interested in very simple tests. So actually will be tests which will be some functions of our observation. And we will say that the test rejects, the test accepts HI if this function is non-negative, and it rejects HX if this function is negative. So this is very simple. And basically, starting from this, we can easily bound the probability of wrong detection. For instance, look, assume that the nu behind the observation was A of X. Okay? So the probability that we rejected the hypothesis HX, given this, will be bounded by just like in the Kramer way. So we will just compute the exponent of minus 5, expectation of the exponent of minus 5 of omega, and basically it will be this integral. This will be the upper bound for the probability of wrongly rejecting the hypothesis HX. The probability of wrongly rejecting the hypothesis HY will be exactly in the same way. We can write it this way. So this is the interest of this aggregate. The logarithm, sum of logarithms of probabilities. Okay? And basically our last assumption we made about our model when we say that it's good, it says that, okay, these guys are convex and phi, always, they are, what we want, they're going to be concave and x and y, meaning that, okay, they are convex and phi and concave and y, meaning that this aggregate will have a saddle point. Okay, but we can minimize it in phi and maximize it in x and y, and this is the main result, basically, of what I'm talking about. So it's saying that indeed this function will have a saddle point, okay, and we will define the value of the saddle point. We will say that it will be 2 logarithms of epsilon star, and basically epsilon star will be exactly the upper bound on the risk, okay, if we use the detector phi star, which is the saddle point, the phi component of the saddle point of this big phi. This will be the maximum probability of rejecting hypothesis in our problem. The second part of the result is that, okay, this is the upper bound for the probability of rejection, and this upper bound is not bad. Meaning that if we have whatever test, okay, of testing just a simple hypothesis, that our signal was X star, which is the X component of the saddle point. And the second hypothesis will be, our signal was Y star, which was the Y component of the saddle point. Okay? And if there is a test of testing just this simple hypothesis between X star and Y star with probability of errors like smaller than 2 epsilon, then our test will provide the probability of the error, which will be 2 square root of epsilon. Okay, in a moment we will see that it's, okay, there is epsilon here, square root of epsilon here. We will see that it's not very bad. And basically the optimal test, we can easily see also that the optimal test phi star, okay, is just the likelihood ratio test between these two simple hypotheses. So we compute the X star and Y star components of the saddle point solution. And we have to do the likelihood ratio test between these two values. Okay? Now, it's not in this abstract form. I'm afraid it's not very clear, but let us see what does it mean in some examples. Okay? So let us assume a simple situation that actually our space is the space of distributions. Okay? So our M is just the set of discrete distributions with M, small m components. All right, so it's the interior of the standard simplex. Okay, So now what we have to do, we have two sets of distributions. Okay, we have the set of x and the set of y. We have their images. So some, for instance, we can consider the like noisy observations or some truncated observations of our random variables, which will produce the set A of x of distribution, B of y of distribution, for which we have drawn the observation on it. Okay, and what we have to do to construct the test, we have to do something very simple. We have these two sets. We have to compute the points of these two sets, which has maximum Hellinger affinity between them. Okay? So this thing is exactly the Hellinger affinity between two distributions. We have to maximize them between these two convex set of distributions. Then we have computed this point.
The Hellinger part, I mean, is this an output of your computation? I mean, we didn't see it before, right? So what is that? It's like something you can. This is equivalent to computing
this is exactly what we have to do. Okay, this is the x, y component of the saddle point solution.
For this functional that you showed us before, it
Yes,
actually. Okay.
yes, because you obtain this just switching the maximum and the minimum. All right, and the minimization with respect to phi is very simple, and then you can maximize with respect to x and y, and you obtain exactly this problem. Okay, and basically what we have to find these 2 points which has the maximum Hellinger affinity, and then do the ratio, the likelihood ratio test between these 2 points, and actually the risk of this test between these 2 points, and for this reason it will be also the risk of separating two sets, capital X and capital Y. It will be exactly Hellinger affinity between these 2 points. So the picture is like this. So you have 2 sets of distributions. They are images here in the image space. And basically what you're interested in is to find 2 closest in Hellinger distance points between of these 2 sets, and do this likelihood ratio test between these 2 points, and this will be the test value.
So if you were to use a different relaxation than the Markov one that you choose, for example, so at some point you use Chernoff.
Okay, this is a very good question, because basically the optimal way of doing the testing would be just find 2 points, 2 closest points, 2 points we have the highest test affinity. I mean closest points in L1 distance. Okay, this will be exactly the optimal test. The problem with this test is that, okay, we're talking now about one observation. Okay, you couldn't generalize it to multiple observation situation, because if we are able to compute, for instance, for just one observation, the L1 distance between 2 sets of distribution, there is absolutely no visible any algorithm which will allow us to compute the L1 distance between the products of distribution. So it will be very hard computational problem. But we will see that with Hellinger affinity, it's much better.
And could you actually find, sorry, I'm sorry, so could you find like another one where you would get, say, the KL divergence, or some chi-square divergence, or some easy to compute divergence? I mean, at which step would you have to change that? Like where you use the Chernoff type bound?
I will talk about this in an instant. So what we want is the mechanism which will allow us to compute easily the distance, the corresponding distance, whatever distance you like, between these 2 sets when we have the product distributions. All right? So just in a second. So the second situation is very classical. Sorry, I just said, I didn't say before, but basically this trick with a Hellinger affinity, it was known to Lecam probably, and Lucien Berger used it in some context. Okay, so there are smart people who knew for a very long time about this. Okay, so this one is basically the self-evident situation when actually you have a noisy, we have the white noise observation. So we have our parameter is mu is the mean of the normal distribution. Okay, so we have this observation scheme, and basically in this situation, the previous scheme amounts to computing 2 closest and Euclidean distance points of 2 sets in the image space, and then actually our test is the likelihood ratio test between these 2 points, and you immediately see that actually we can provide some beta estimation for the probability of the wrong detection using the distribution function of the normal distribution. So basically in this case what you do, you just have like this, so you have two sets, okay, two convex sets, you find two closest points of these two sets, and basically this will be your detector, okay, and you compute the scalar product of this vector with your observation, and you compare it to the value at the middle of the signal, okay, and this is the optimal. Basically, this is the optimal set. Here, there is no defect, there is no suboptimality, and basically, it's clear that separating these 2 points, okay, you will separate any convex set. I mean, in this half plane or in this half plane. All right. Finally, the last example, and basically, unfortunately, we know only 3 examples of this good observation scheme. They are the last example, and basically, you see that you have the distribution scheme, and you have 2 limit cases. You have Gaussian case and the Poisson case. Here, this is the last example, the Poisson distribution. And basically, so we are drawing Poisson random variables with the mean, which is a linear function of some of our signal, and basically what you get here is like in the distribution example. So what you have to do is to find 2 closest in Hellinger distance points of 2 convex sets, and then the optimal value of the criterion will be this Hellinger distance, squared Hellinger distance between the sets, and okay, the set will be likelihood ratio test between the 2 points, and the probability of the wrong detection will be bounded with the exponent of this minus Hellinger distance between the 2 points. Okay, now this is why you need basically working with Hellinger distance. This is exactly the situation. So this good observation scheme you can demultiply. So if you have multiple independent observation, okay, you can easily verify that actually it transforms very easily to this situation. So the simple situation is that we have multiple observations from the same distribution. But basically you don't need the same distribution. But just to save notation, so imagine that you have multiple random variables omega k drawn with this probability. Okay, and so now formally you have the direct product of observation spaces, you have direct product of probability measures, and you can easily verify that, of course, this direct product of densities will result in the sum of, because phi, they are logarithm of densities, so the direct product of the densities will be just the sum. Okay? So if we have many observations drawn from the same distribution, and if we want to decide if these observations were drawn from mu, which belong to the image of x, or with parameter mu which belong to the image of y, actually we can apply the test, which is very simple. It's basically if phi star of omega k is the optimal test for one observation, the optimal test for multiple observation scheme, it's just sum. Okay, and the probability of error detection is just the probability of error detection for one observation to the power k. That's it.
Can you relate to some notion of sufficient statistic? Because if you have a product distribution on exponential families, you just basically boil it down to one sufficient statistic for everyone.
Probably. Sorry. I don't know much about this exponential family. Sorry. Okay, so basically we can reformulate now this the theorem for the case of multiple observations. This optimality statement of our theorem, which says, you recall, we pass from if there is the test which detects with probability of error bounded with 2 epsilon, then we will detect with probability of error bounded with 2 square root of epsilon. And here, basically, what does it mean? If we want the same probability of wrong detection, okay, how many more observations will we need with respect to the optimal test? Okay, if we apply our test. And basically what it says, this is, if there is the optimal test, we will detect with probability, with the risk, with risk epsilon, with bar k observation, then for k plus observation we will be done. And basically this kappa plus, you can see then epsilon is large, this kappa plus becomes like twice kappa. Okay, so this suboptimality is bounded with the factor 2 times something which is not very. Okay, now the case which is much more interesting because it was just separating two convex hypotheses. Now the case of multiple hypotheses, basically you assume that you have many sets, many convex sets, and you want to separate, in a sense, to decide between these multiple hypotheses and given an observation, the same kind of observation, and basically what we will do, we will proceed pairwise. Okay, so, okay, now if you have a capital L hypothesis, you will need order of L squared pairs. Okay, you will need order of L squared pairs, and you will just, to test all the hypotheses pairwise, and basically what you come up with, so each time you test two hypotheses, you will reject one of them. Okay, and you finish with the list of the hypotheses which are not rejected. And basically what you can say that the error, the reliability of our detector, so meaning that what is the probability to have rejected the right hypothesis? It will be bounded by this, by the sum of probabilities of wrong detection in each pair. Okay, so basically you can immediately compute you immediately get the union bound here.
So really you're comparing only L of them, right? You're always, you do two and you keep the winner and then you do another one against the winner, etc.
Okay, it can come to order of L squared, but okay, you may be smart. It's in each practical situation. You should, this is the point where you have to be smart, to economize it. So just look at our application and basically we come back to our problem. So what we need here is just to decide. So we have our observation drawn from this, from the distribution with this parameter, and basically we want to decide between the hypothesis H0, that there was no signal, and the hypothesis that the signal was present. And basically, okay, what we get, we will define the epsilon profile of the test, and this epsilon profile means that if this is the values of parameters of rho, which allows the epsilon probability of wrong detection, whatever is the signal which is larger, with amplitude larger than the rho, and whatever is the nuisance parameter in our sample. Okay, and we will say that our test is rate optimal if there is no rate, if there is no test which has a kappa rate optimal, which if there is no test for which the rho profile is smaller than some kappa to the power minus 1 than our rho profile. Okay, and basically what we can do, it's very simple in the Gaussian case, applying our strategy, because we want to decide between the hypothesis there was only nuisance and the set of 2n alternatives, okay, that were signals with signs plus and minus of this type, okay, and this is just like this picture. So imagine this is the nuisance hypothesis, pure nuisance, this is the signal hypothesis, and basically we have to separate them, to move them until this distance between the two sets will be like the quantile of the normal, twice the quantile of the normal distribution with the corresponding probability. So this is exactly the first line of the slide, is the realization. To find the corresponding level, the minimum level of signal which will be detected, you have to solve this optimization problem, which is fortunately convex, and then you can construct your detector. So basically, what you see here, what you can say that the suboptimality of our test is just a ratio of 2. So there is no test for which this kappa factor will be better than this ratio, and you see the quantile, this epsilon over 4n, because there are 2n hypotheses and quantile of epsilon over 2. So I will skip just to show you some pictures. So this is an experience. So what is very nice for this, because people knew about this for a long time, but apparently no one tried to do some numerical computation, and this is very nice to play with it. So just in the convolution model, you just choose whatever kernel you like. So you have some parameters of the experiment, so you have like the kernel of length 60, and you have 100 observations, so the signal will be of length 155, and you assume that the signal is Hölder regular. Okay, this is your assumption about the nuisance, excuse me, the nuisance is Hölder regular. And then you just put it on the computer and you see what happens. So look, here there is the raw profile. So this is the minimum level of the signal, this coefficient in front of the signal, which will be detected by our test. This is in red. And below is the baseline profile. So just below is the probability of wrong detection just between two hypotheses for the signal at each point I. You just forget about the union bound and you compute the best test of deciding between two hypotheses. Okay? And the ratio between the two is like this. So basically you see that by factor 2, you are right. You are good. And here you see, actually you can see everything. You can see here is the signal plus nuisance. So this is the different signal. Basically this is the signal, the worst situation. This is the signal which should be detected in the Gaussian noise. And here you see typical observation. And basically it's not easy to see what are you looking for in the signal. And what you're looking for is something like this. This is the optimal detector. Okay, so you have to do the scalar product of the signal with this one and compare it to some threshold. Okay, I will stop here.
Thank you very much. Short question.
So it looks like what you are doing is suboptimal because it could be that the optimal test has a risk of epsilon, but your test will get only square root of epsilon. And this is because you are optimizing basically the product rather than the sum, right?
This is because I'm using Hellinger distance instead of...
No. I'm talking about the main theorem where there is absolutely no Hellinger distance.
No, because this is because I use the exponential bound for the probability. All right.
No, it's because you optimize the log of the first bound plus the log of the second bound. So
this way
you
you probably can get a factor of 2, all right? Because I optimize the sum. But the square root comes from the fact that Hellinger affinity is square root of product. And the Hellinger affinity is the sum of square root of products of probabilities, right? And the test divergence is the sum of minimum of two probabilities. And actually, in the bad situation, which basically never happens, this square root of the product may be like sum of square roots. If one is big and the other is small. Okay? It can be a sum of square roots instead of sum of probabilities. So this is where this square root of epsilon comes from. But in practice, basically what you see that both are small, basically. And actually you don't see this factor, the square root of epsilon factor in practice.
It sounds like you could come up with an example where the gap is actually there.
Yes, sure.
Okay. And
But, well,
right. And then my second question is that, so in the main theorem you were saying that the optimal phi that you get is the likelihood ratio test. But do you assume that this guy is going to be in your family F? Or what? Why? I don't see why.
Yes, it's
okay.
because our family F, it's the family of logarithm of ratio, density ratios. So, and we assume
okay,
that all the densities are on strictly positive, so it's
Okay, thank you very much. So now we have a break.